Thank you for waiting.
Back Theodore Drivas from Stony Brook University, and he will give the last part of his mini course on mathematical aspects of turbulence.
Okay, thank you very much. So last time, or last 3 times, we covered these topics having to do with fully developed turbulence and the Kolmogorov and Onsager ideas in that context. This time I'm going to transition to a different topic, namely, how does turbulence get dynamically produced? And I'm going to describe a certain controlled setup that actually Kolmogorov proposed to study this problem. If I had more time, and I was initially planning to do this, I would have also talked about certain stationary states of the Euler equation and dynamics near them, but I think I don't have time for that. Okay, so this is going to be about transition to turbulence, and this is a quote from one of Arnold's papers, saying that Kolmogorov considered his work, the one that we discussed, those ideas to be non-mathematical because they rested on assumptions that couldn't be a priori proved from the dynamics. And he wanted to explain what he saw and what he theorized from some first principles. And he wanted also to use theory of dynamical systems. So he believed that that was the right approach to studying these ideas. So let me just now give you a cartoon of the type of thing we would like to understand. So consider an ODE. So U evolves according to some vector field F of U. And this ODE evolves in some phase space, some linear space H, and F just maps H to H. Now there are 2 cases that let's consider. One is finite dimensional case where H is something like RD. And then there's also the infinite dimensional case, which is the fluid setting, where H is going to be a Hilbert space. Okay, so 2-dimensional fluids. So by the way, everything I'm going to say today is restricted to 2 dimensions. And 2-dimensional fluids actually fall into this category where H is either the space of L2 divergence-free vector fields, or it's the space of H1 divergence-free vector fields. And which one the equation forms the dynamics on depends on the regularity of the external force. Okay, so this is just a formal definition. Okay, so what we're really interested in is the long-time behavior of solutions of this ODE. And typically in problems of interest, this vector field F is parametrized by some parameter, let's call it mu. And the long-time behavior of the system will depend very sensitively on the value of this parameter. Okay, so what I'm going to describe now is very much a cartoon of different stages the end states of this ODE can take as you vary the parameter mu. And this cartoon is paralleled with something I'm going to prove rigorously, or at least outline the proof in the context of Navier-Stokes. Okay, so the first stage, if you will, is when this parameter mu is small, maybe smaller than some critical, let's call it mu1, the ODE has a unique stationary solution. Let's call that solution US. It just satisfies that it's a 0 of the vector field F mu. And this stationary solution is stable and it tracks all orbits. So any other solution starting from some initial data asymptotically approaches this stable stationary state as time goes to infinity. Okay. Now, as you increase the value of this parameter mu, maybe there's another range here between mu1 and mu2, say, such that new stationary states of the ODE appear. Let's call them US2, US3, and so on. In this range, the original stationary state from stage 1 loses its stability and exchanges, in fact, stability with these new guys. So when it loses its stability and these new ones emerge, we say a bifurcation has occurred at this parameter mu1. And like I said, typically these new solutions that emerge are stable, and they each have some basin, perhaps small basin, but some basin such that they attract locally solutions that start nearby them. Okay. The next stage that may happen in some systems is that as mu is increased further, say now between mu2 and mu3, a Hopf bifurcation occurs. So now the flow doesn't become stationary as time gets long. Instead, it converges onto some periodic orbit of the system. So some time periodic solution. If you take it away from the given solution you're interested in, that difference asymptotically goes to zero. And it just should be noted that these parameters, mu1, mu2, mu3, there are things that are very, system specific. You can't compute them a priori. You have to do some detailed analysis to figure out where these points actually are. And now one could have a system that undergoes Feigenbaum type cascade of period doubling, where you have, as you increase this parameter, say periodic solutions of just increasingly large periods here, let's say 2, 4, 2 to the j. Or you could have a different type of behavior emerging, where when you push mu above this mu3 region, you have some invariant tori arising. So you converge onto a quasi-periodic solution of the ODE. This is a solution that essentially has, let's say, finitely many frequencies here, and you can think of in phase space living on the surface of a torus. Okay. Now, just a small remark, when the flow is quasi-periodic, it may look chaotic, but you could analyze the signal and figure out that there are really only finitely many frequencies activated. So there are ways to distinguish it from chaos in a sense. And now the final stage that I'd like to discuss is when the flow is really chaotic and it looks in some sense really high dimensional and in some sense completely random. And here, what can happen is that orbits are attracted to some compact region of phase space X as time goes to infinity, in the sense that, in the topology that your dynamical system is endowed with, the distance between the orbit and X goes to zero. So here's just a cartoon of it. And this X is an invariant subspace of the phase space H. So if you start in X, you stay in X. And in fact, you can have a dynamical system on this attractor X. And even though my drawing here is very regular, it should be noted that this set can be actually extremely complicated. Some fractal set with some complicated geometry, making this space non-smooth and so on. So this is somehow a cartoon of what you might expect. So what we discussed in the last 3 lectures are these features of turbulent flows, namely these structure functions, scalings, and energy spectra, exponents. And I think Misha asked a question, which maybe I didn't really address well last time, which is what's the connection between, these Onsager type statements about regularity and Kolmogorov's assertion about spectral scaling. And the point is that the regularity statements are really statements about very small scales, asymptotically small scales. How do the functions look? But they don't say anything about a finite range of scales over which you see some kind of power law behavior. So the power law behavior implies the regularity, but if you live in some space, the one Onsager talked about, doesn't mean you look like Kolmogorov envisioned with these spectra and a scaling range. And the point is that maybe if you understood well this attractor in this turbulent regime, somehow the properties here would tell you that solutions should develop that type of feature. But that's very much a long way off, but perhaps it's one way to rationalize that part of the Kolmogorov theory. Okay, so were there any questions about that, or?
So there are several scenarios, so through cascades of Koch bifurcations. I think that it was Landauâ scenario, true,
Yeah.
Koch bifurcations, but my impression was that this scenario was somehow finally recognized as unrealistic, that that's something that does not happen with real fluids. Is it so?
I think that is true, and I think actually, well, the status of what we observe to happen and what we think happens is very much not settled. So maybe I'll talk about what we know happens and what we don't know happens shortly in this model. Okay, so the model that I'm going to discuss today is one that Kolmogorov proposed in this analysis seminar in 1958, and it's perhaps the simplest possible setting where you could really hope to try to quantify this dynamical transition as some parameter, which ends up being the Grashof number or the Reynolds number, I'll explain in 1 second, is varied. And at one end of the parameter regime, you have laminar motion, and at the other end, supposedly you can maybe describe turbulence. And so the setting is that you consider now a two-dimensional fluid where you have a period of 2 pi L over alpha, some number between 0 and 1 in X, and 2 pi L in Y. So alpha, L, these are all positive numbers. So we're on this rectangular torus here. And you consider now the Navier-Stokes equations, which we've seen before, but let's add an external force with strength gamma. Incompressible still, and say mean zero data, which is propagated by the equation. So let's just say mean zero. So the geometry is this. You just have this rectangular torus and some motion of the fluid inside. Now, Kolmogorov's problem was to take a very specific forcing, which turns out to be quite simple to analyze, at least in a certain regime when the Reynolds number is small, so in the laminar regime. This forcing is an eigenfunction of the Stokes operator. That's just the projection onto divergence-free velocity fields of the Laplacian. So this is acting on a velocity. And this is a positive operator because there's a negative sign here. And so this F is chosen to satisfy this equation. So it's parametrized by this eigenvalue lambda, and that's it. Now, these eigenfunctions of the Stokes operator can actually just be constructed from eigenfunctions of Laplacian. So you take the perpendicular gradient of an eigenfunction of Laplacian, which is mean zero, and you get an eigenfunction of Stokes. And these are in one-to-one correspondence. So an example of what one of these might look like is a shear flow, either in the y direction as a function of x, or in the x direction as a function of y. So this is something that looks like this, or like this. And those are both Kolmogorov forcings that you would put on the right-hand side here. So now let's see why those are particularly simple. Oh, so this is actually this is a paper by Arnold and Meshalkin. This is Kolmogorov's problem. He took eigenfunction, which is sine y comma 0 from the previous page. Okay. So now let's see why these forces are particularly beautiful to work with. Well, if you introduce the vorticity, now I talked about this in the first lecture and not so since, but the vorticity in 2 dimensions is actually just a scalar, positive or negative. It represents something that's pointing out of the plane if the motion is planar. And that component is just given by the perpendicular divergence of the velocity. So it's this expression here. Now, we derived, or at least I stated, how this moves. So the vorticity is transported by the fluid velocity, it's diffused by the viscosity, and it's forced. And in 3 dimensions, you would have an additional term here that represents the stretching of the vorticity by the velocity gradients. But that term is not present in 2 dimensions because of the symmetry. Now, this force, again, I remind you, is an eigenfunction of the Laplacian with eigenvalue lambda. So if you introduce now a stream function, remember this U is just a 2-dimensional divergence-free velocity field. So we can represent it by a scalar function psi, the grad perp of it. then this equation just reads this right here. So I've introduced this Poisson bracket J, which is grad perp of A dot grad B. And now this nonlinearity in terms of the stream function becomes this Poisson bracket of psi with its Laplacian, because if U is given by this, the vorticity, which is the perpendicular divergence, is the Laplacian. So this is now the system that we want to study. And immediately we can identify a stationary solution. So in particular, if we take a solution, if we take a stream function, which is an eigenfunction of the Laplacian, so that this is actually proportional to lambda psi, then the Poisson bracket between psi and itself is 0, because it's grad perp dot grad of the same thing, so it's 0. So any eigenfunction of Laplacian annihilates the nonlinearity. Also, eigenfunction of Laplacian plays well with this dissipative operator, because you just apply Laplacian twice. And if it's time independent, this is dead. So in particular, if you just scale correctly the eigenfunction of Laplacian, the same one as the force, then this dissipation actually directly balances the force, and there's no contribution from the nonlinearity or the time derivative. So this is a laminar solution, a laminar steady state of the fluid. And we'll see why it's called laminar in a second. But one important remark is that this stationary state exists for all values of viscosity and gamma. I mean, it's just always a solution. But as we'll see, this solution is sometimes stable and sometimes it can go unstable depending on the value of these parameters. Okay. Now the velocity of this solution is just the perpendicular gradient of this, which is what I called F lambda before. And explicitly in this example, the velocity is just this shear flow. So it's like sine y, like this. Okay. Now, as I alluded to, this stationary state is actually the unique stationary state and is globally attracting if this parameter mu, which in this problem is the strength of the force gamma divided by the viscosity square, if that parameter is small, so that could happen when the viscosity is very large, for example, or gamma is small, then this fixed point is the unique global attractor. So it attracts all orbits. And this parameter mu is going to be our order parameter. So as we increase it, we're going to see instability, new stationary states. You can also see periodic and time states. And then hopefully we can understand turbulence by sending this parameter to infinity. I should remark there is one, yeah.
So what is your parameter? Reynolds number? What is your parameter?
Okay, so technically this number is called the Grashof number. The Reynolds number, if you remember, is the ratio of some characteristic velocity, and this is actually based on the force, not the velocity. And that's because the force is a natural parameter in this problem that you can input. There are ways to relate this to a Reynolds number. You can sort of make sense of that. And then mu is roughly Reynolds number square. That's the relation.
Okay.
So there's one trivial case of this setup. The trivial case is when you force with an eigenfunction corresponding to one of the smallest eigenvalue of Laplacian. So in that case, you call the force the gravest mode. It's sort of the largest scale thing that fits in the domain. And this solution is in fact the unique global attractor for all values of mu. So there's no transition to anything. It's just always stable. And the dynamics are always trivial in the sense that they just contract onto that one fixed point. So that's just something to keep in mind. Actually, what we're going to study is this force on a torus, which is not square, on which it would be one of these gravest mode, but instead a torus, which is rectangular. And now there are lower modes that go like this in X. So it's not on the first shell. Okay. So here's a picture of an actual physical experiment trying to explore this setting in a paper by Abakov in 1983. So this is apparently it's forced with some electromagnetic forces, and there's some way that the fluid is interacting with them, so that you can really produce this type of sinusoidal forcing profile. And what you're visualizing here is the velocity. So the velocity is aligning with that sinusoidal force, just like it did here. That's the aligning laminar state. Now, as you increase the parameter, suddenly this thing is becoming wavy. It's not aligned with the force. And here it's settled down into some sort of permanent regime of a wavy type solution. So that's the real world. And actually there are, I took this, but there are more realistic, more modern experiments that have even better images, but I thought this was interesting. Here's virtual reality. This is a computer simulation. What you're visualizing here is the vorticity, and here it's the stream function. So these lines here represent motion of particles. Particle will just go along this line, and the vorticity is sort of the local spin of the fluid. Here's the laminar regime when the parameter mu is small, and this is a stationary state of the fluid now. Now I increase the parameter just a little bit past the critical value, and here's another stationary solution that bifurcated off from this one. This one has these little vortices, and the streamlines are now wavy. So it looks similar to this. Okay. This has forcing cosine 5y, and I did this very easily because Navier-Constantinou put his very nice code online, so it's very easy for anybody to actually run these two-dimensional turbulence simulations. Okay, so now I want to just put this quote from this paper by Arnold, Kolmogorov's hydrodynamic attractors, because it summarizes the state of this problem at the time it was written. And actually, there hasn't been very much development since then, but I'll make some remarks later about that. So he just says what we just said. If the Reynolds number is small, the steady laminar flow emerges, and then that flow loses stability as Reynolds number grows. And Kolmogorov's program is to rigorously study these bifurcations of the attractors and the dependence of these attractors on the growing Reynolds number. And the first step in this program, the instability, was done by Meshalkin-Sinai. And here he says bifurcations have not been completely understood even now. He doesn't mention a work of Yudovich, which actually is the next step beyond Meshalkin-Sinai, which is, I think, a very important work in this circle of ideas. So the first bifurcation is actually completely understood by the work of Yudovich. So we'll discuss his theorem and some of his proof here. One interesting thing is that when Kolmogorov first proposed this problem, very little was understood about it, and he asked the question. So if you have this sort of period doubling type scenario, if you have even for quasi-periodic flows, if they occupy 2 tori, 3 tori, 4 tori, subsequently as you increase this parameter mu, he asked the question, is it possible that over a finite range of the mu parameter, you could undergo infinitely many such bifurcations? And this is, for example, what happens in the logistic map picture, where just in a finite range, you undergo infinitely many such bifurcations.
But I'm not sure that Kolmogorov was aware of the logistic map, actually, of this double bifurcation cascade.
Oh yeah, I don't know. I'm not saying he was aware. I'm just saying that that's what happened. Yeah.
It was kind of introduced substantially later, in 60s, maybe 70s even, yeah, in the 70s. So
I see. Well, okay, so this piece of information, I got it from this paper by Arnold. So apparently he asked this question. Whether he was aware of what happens in these iterated maps, I don't know, because first of all, the timing, I'm not sure exactly when he asked these things. It could have been later than the date that he proposed the problem. But he asked it, yeah.
Certainly the Hopf bifurcation was well known, and so that's why probably Landauâ and maybe Kolmogorov so suggested that scenario, but not the Dublin bifurcation scenario.
I see. So in response to this question in the 80s, Ladyghenskaya and Ilyashenko proved that this couldn't happen for two-dimensional fluids. So in particular, they provided an upper bound to the Hausdorff dimension of the global attractor of the system, which can be proved to exist for two-dimensional Navier-Stokes. And this upper bound takes this form where I've changed my notation from mu to g, which is the Grashof number. And so here I've defined it in terms of the force. And actually, these were early works.
Paper by
Wasn't
there also a paper by Smale?
By who?
Wasn't there also a paper by Smale?
Oh, I don't know. I don't know.
Okay, I'll look it up.
Okay. So these earlier works provided the qualitative statement that the attractor was finite, was finite dimensional, but the bound here is the sharpest one known, was produced by Konstantin Foyash and Tamam in the later 80s, and this bound is expected to be sharp in the sense that this dependence on the Grashof number is in agreement with Landau's degree of freedom argument to estimate how many degrees of freedom a turbulent flow has. So I don't really have time to go into that argument, but the basic idea is Landau used elements of the Kolmogorov 1941 theory as it would be applied to two-dimensional turbulence, which is actually something called the Kraichman-Batchelor theory. There's an associated smallest length scale where the viscosity now effectively dissipates not the energy, but the enstrophy. So there's some discussion that should go into this, but anyway, the point is that the energy is not the relevant quantity to determine these scaling laws in two dimensions. It's something called the enstrophy, which is the L2 norm of the vorticity. So now understanding how that transfers, there's an associated length scale like the Kolmogorov scale for the energy. This is the Kraichman scale for the enstrophy. And that's the smallest scale where you have some appreciable motions. That's the idea. So this bound is really just this length scale underneath L square. So this is like how many little boxes of this smallest scale L you can fit inside the big box in two dimensions. And that corresponds directly with this. So anyway, that's a, we'll talk more about the sharpness or lack thereof.
Sorry, I just have a small question about like the parameter mu, which is related to the force. So like for fluid, it's a force by line. It's like a pressure, isn't it? It's not a punctual force that you're dealing with.
But could you repeat that?
Like
it's not
the force is not a force. It's a pressure.
Oh, it's a force. Why a pressure?
It's applied to point.
It's a forcing on the right hand side of the equation. It's not like a gradient force. It's a force. I'm not sure the. Maybe we could come back to it at the end.
Okay.
Okay. So then a subsequent question after it was understood that the attractor was really finite dimensional is does the minimum of the Hausdorff dimension of the attractors, there could be many attractors, so there's this one global attractor, but it could have components which are locally just attractors of some region of phase space. So if you think about minimal attractors, which are ones that have that contain no smaller attractor, Kolmogorov asked the question, does the minimal Hausdorff dimension of such things grow as Reynolds number is increased? Okay, so the picture we're trying to build up is this one. You have at 0 Reynolds number and small Reynolds number, some unique fixed point attractor. This is like the first phase. Then you have some critical Reynolds number, after which this thing becomes unstable and new stationary states bifurcate from the original one. This was Meshalkin-Sinai and Yudovich, as we're going to see. Then something could happen, things happen inside here. We're not sure what. It could be doublings, could be quasi-periodic thing, could be many different types of phenomena. It's not very well understood. So I put question marks in these phases. But then there's this theoretical infinite phase when this parameter really goes to infinity. And in that regime, in 3 dimensions, you would expect the emergence of things like Kolmogorov 1941 theory, Onsager's theory of ideal turbulence as governed by weak solutions, rough solutions of Euler. And in 2D, there are corresponding theories by Kraichman and Batchelor. So this is like the infinite phase. And so in this conjecture, Kolmogorov is basically saying that as you increase this parameter, the dynamics really do become increasingly high dimension. So somehow turbulence is an infinite dimensional phenomena. There's motion at all different scales. And he's saying here that this picture of it being infinite dimensional should be built up through this type of procedure. And right, so that's this arrow here saying, yeah.
But did he still suggest that this statistical model that he actually developed, comes ultimately from deterministic equations, from the deterministic model?
I think that was, well, okay. I think I don't know what he, but there is some hope that could be the case.
It seems that there is this big jump, and somehow I don't see how his statistical ideas connected to the ODE ideas.
Well, I guess it would be connected through long time averages of the behavior of the solutions on the attractor.
But
there's no rigorous connection at the moment, but the hope would be that
it happens already in this intermediate stage, I guess, when you have this strange attractor of finite dimensions, then there is some stochastic behavior, but in this situation, we can kind of believe that maybe it's not so surprising that this stochastic behavior is can be described by deterministic systems, comes from deterministic system, but for the fully developed turbulence, it is still something that you, for instance, now would anticipate that there is a deterministic mechanism behind the statistical models. At this stage, today, would you?
I think there could be, yeah. I wouldn't say there's no hope for that to be true.
Interesting.
Yeah. I mean, I could be wrong. Yeah. So, okay. So in phase 1, let's just see what the motion looks like. So if I start with initial condition like this, and I'm forcing with that sine y force, then just as time goes to infinity, this converges to the force. So that's this trivial type phase where the fixed point attractor is the global attractor. And right, so the theorem is that there exists some critical value such that for this Grashov number less than that critical value, this is what happens. And remember that if this force is the smallest force, I mean the largest force that occupies the domain, so it corresponds to the smallest eigenvalue, then this statement is true for all mu. Okay, so that's the one caveat, the one case where this is always true. Okay, so then phase 2, which is this first bifurcation, was proved really by Yudovich in 1965. So the statement is this: let's take a torus which is slightly wider, which is wider in x than it is in y. So it's a rectangular torus like that. So that's this parameter alpha. Now consider Navier-Stokes forced with this eigenfunction. Then there exists a critical Grashof number, which is a function of this alpha, and it's monotonically increasing with alpha. As alpha goes to 0, this thing converges. So this is for like a very, very stretched out torus like that. This goes to just some number, square root 2. And as alpha goes to 1, where it becomes the square torus, this goes to infinity. And that's in keeping with the result that this is the lowest eigenfunction on the square torus. So it's globally stable if you start there. So this is just saying that, quantifying how that happens when you stretch the torus out. And furthermore, this critical parameter has the property that if mu is less than it, the laminar state is unique and stable. If mu is bigger than it, the laminar state is unstable. And this was actually first proved by Meshalkin and Sinai. And then finally, if you have a small deviation from this critical one, then there exists a family of stationary states that bifurcate from the laminar one that exchange stability. So they're linearly stable. And okay. So let's first see what Yudovich is talking about. So this over here is the critical, is right around the critical mu. And this corresponds to a stationary state. So I take some initial data nearby the steady state, and I run to long time, and it settles down to this steady thing. Now I increase the parameter just a little bit. I do the same procedure, and I settle down to this stationary state. This is not something that would move. It's exactly stationary. And you see it has this buckling. It just sort of bends. Now I continue to increase, and this buckling just becomes more pronounced. So eventually it starts to really wiggle. And these are all stationary. So I'm following a branch of stationary states that leave the laminar one. Okay. So let's now talk about the elements of the proof of this statement. The setup is that you take the laminar stationary state that you want to bifurcate from, and let's just take the difference between that laminar state and a perturbation. Let's say that makes up the whole solution. Now, I want this thing to be a stationary state of the full nonlinear problem, okay? So if I just insert this and demand that it be stationary and solve the equation, I find the equation for the perturbation phi. Okay, so the perturbation now satisfies this equation. It's also nonlinear. And in order to prove the bifurcation, we're going to use some bifurcation theorems that I'll say in 1 second. So for those, we need the linearization of this system, which is that. And in fact, we also need its adjoint, but I won't write it. So then this equation and this equation can be read as this. So these are now functional equations in H2, and they're eigenvalue problems. So this is the metric, so Laplace F, Laplace G integrated over the torus. So this right-hand side here is representing this term, okay? So these are now eigenvalue problems for phi. This is a nonlinear one. It's like a generalized eigenfunction. If we construct phi like this, then we've gotten a new stationary solution if it's non-trivial. And this is a linearized one, okay? And so, of course, we're going to use the linearized one to actually construct the nonlinear generalized eigenfunction. So what's the general theory to do this? Well, if you have some equation, g of u is lambda u in a Banach space X, and G has the property that at 0, it's 0, it's compact, it's differentiable at u equals 0, and has a compact derivative, A. So this is the general class of things that we'll consider. And if let's call S the solution set. So this is the lambda and u, which are in R in this space, such that u is non-zero and you satisfy that equation. Then a bifurcation point, lambda star, is just one such that any neighborhood of lambda star comma the trivial solution, there's a point in the solution set. So in any neighborhood, there's a point in the solution set. And it's easy to see by implicit function theorem that bifurcation points have to correspond to eigenvalues of the the derivative A. But in fact, the reverse is not always true, and there are these theorems that basically tell you when it is. So the theorem says that if those properties hold, this is Krasnoshelsky's theorem, lambda star is an eigenvalue of A. If lambda star is an eigenvalue of A with odd multiplicity, then it's a bifurcation point for this equation F. So basically, if we can construct a solution of the linearized problem, and we can verify that the eigenfunction that we construct has odd algebraic multiplicity, then we can appeal to this theorem and thereby construct a nonlinear generalized eigenfunction that gives us the stationary state. And there's a refinement of this by Rabinowitz, which actually allows you to say something more global. You can say that there's a continuous family as you increase the parameter lambda, but let's just use this one for now. Okay, so in order to obtain information on the multiplicity of the eigenvalue, you also have to study the adjoint linear problem, and you have to find an eigenfunction for the same eigenvalue for the adjoint problem that's not orthogonal to the original eigenfunction. So if you can do that, then the eigenvalue is actually simple. And so that's how you can reduce it to that's how you can deduce the multiplicity. And so then you need to find an appropriate setting for which the eigenvalue of the linearized problem would actually be simple. And this is just a very simple idea here that Yudovich uses. Let's say you consider this problem dx square h equals minus lambda h. Well, this problem has eigenvalues which are just k square and eigenfunctions sine kx, cosine kx. So the geometric and algebraic multiplicity of lambda, one of these lambdas, is 2. But if you restrict to even or odd subspaces, then the eigenvalues are simple. So basically, this space X here that you see in the application will be chosen to be some Hilbert space, but restricted to just even and odd functions, and those are respected by the equations of motion. Okay, so that's okay. So that's the idea. We restrict to these subspaces. We apply these theorems with the space H2, even and odd, respectively. G, the thing in the previous theorem, is just this nonlinear functional that I introduced a couple slides ago, and this derivative of that G is the linearized operator L. So now what remains is to actually construct an eigenfunction of the linearized operator. And you can use Fourier to do this. So the eigenfunction is some linear combination of phi n, which is given, say, like this. Okay. And if you insert this into the equations, you can actually derive a recursion relation for the coefficients Cm, which are functions of n. So in particular, okay, it's related to something called d by this factor, but then d satisfies this very nice non-constant coefficient recursion relation. So am is given here as function of m, and k is alpha times n. I just want to give you the general idea of what goes into it. So now, if you want to construct an eigenfunction, you basically reduce it to the problem of constructing solutions of this recursion relation that decay at infinity. The decay at infinity encodes the regularity of the eigenfunction. So it's actually a C infinity function if dm goes to 0 at infinity, because from the recursion relation itself, if d goes to 0, then in fact you know that any power of m to times d goes to 0, just by iterating in the recursion relation. So from this, you can derive the characteristic equation, which is that this continued fraction here this is just notation for this continued fraction, which converges by the properties of am. So it's lower bounded, so this converges. So this continued fraction has to equal this number. And note that each element here, A1, A2, A3, A0, they're all explicitly given in terms of mu and n, so k is alpha n. So they're explicit functions of mu, n, and it depends on m in this way. Okay. So now the difficulty is only to construct a real root of this equation. If you do so, then the dn defined appropriately solve this recursion relation, and therefore the phi n is an eigenfunction with this eigenvalue mu. And so Yudovich has an argument to prove that, in fact, there exists exactly 1 over alpha, the floor of this number, many real roots to this equation. And each one, he proves, is simple in the subspace of odd and even H2 functions. Therefore, each one is a bifurcation point of the nonlinear system. So you have a branch of stationary states that correspond to each one of those roots of this equation. And moreover, he gets those asymptotics that I stated in the theorem. So he understands how this thing depends on the parameter alpha. Okay, so are there any questions about this? Okay.
So how complicated is that? So is it just some? So it is some explicit algebraic analysis. It is what is that?
Yeah, it's a. I actually wrote up some careful notes of what he did. I can send them to you. It's explicit analysis. It doesn't require any sophisticated tool, but it's just a very clever manipulation of these continued fractions.
It's strange that Arnold didn't know about this work.
I also found it strange because of the date of the publication of that quote. This happened way before that. So I don't know why he didn't mention it there. Yeah.
Could I ask something?
Yeah.
Could you repeat again the idea of the even and odd?
Oh, so yeah, so you have here this eigenvalue problem, and the eigenvalues, everything is explicit, the eigenvalues and the eigenfunctions. And here the multiplicity is 2, right? But if you restrict to just even or odd subspaces, then you kill one of the eigenfunctions, one or the other. And then in that subspace, it's a simple eigenvalue.
Oh. Thank you.
Yeah. Okay, so now.
But in the final qualitative result, the even or odd doesn't matter.
Well, yeah, so all that happens is that you have bifurcations that are even and bifurcations that are odd. Just to prove that there are bifurcations, you restrict to that subspace. But then for the actual physical statement, what you've constructed are new stationary solutions that have those two symmetries, branches of them.
Okay, so both occur.
Both occur.
Okay.
Yeah. Okay, so now in the remaining time, I don't have very much more to say, but I'm going to talk a little bit about this phase infinity, which is the fully developed turbulence. And I'm just going to focus on these conjectures that Kolmogorov enumerated. So this is recorded in Arnold's books and various places. I've just said them here. So there are essentially two conjectures. There's a weak one and a strong one. The weak one says that as Reynolds number increases, there is a minimal attractor whose dimension grows in that limit to infinity. The strong one says that every minimal attractor has unbounded dimension as that limit is taken. Okay, and it's an interesting point here that Kolmogorov in fact suggested that the answer to the weak one was true, but he had some doubts about the answer to the strong one that says every attractor grows in dimension because of some experiments on delayed loss of stability. And I'm actually going to make some remarks in just a minute about this strong conjecture and some possibilities there. Okay. So the only theorem that I know about in terms of a lower bound on the attractor is one by Babin and Vishik. This actually, I mean, is based on the work of Meshalkin and Sinai on the instability. The idea is that, okay, we have an upper bound, which comes from functional analysis estimates on the equation. So that's this upper bound we discussed early on. But now, how do you get a lower bound? So the lower bound actually comes from the fact that if you have an unstable fixed point, then its unstable manifold is contained in the global attractor, right? Because the global attractor is defined as all like bounded complete orbits. So orbits that are defined well as you go to negative infinity in time, as well as positive infinity. And that unstable manifold exactly has that property, because if you go to negative infinity and you're on the unstable manifold, you converge onto the fixed point. And if you go to positive infinity, you go potentially somewhere else on the attractor. So that's actually embedded inside the attractor. And therefore, if you have a bound on the dimension of the unstable manifold of some unstable steady state, that provides a lower bound to the dimension of the global attractor. And therefore, it provides a lower bound to the dimension of some minimal attractor. So it would correspond to the weak form of the Kolmogorov conjecture. And this bound, you'll recognize the integer part of 1 over alpha here, because it's the same thing that came up in Yudovich's argument. The point is actually quite simple. If you have an elongated torus that has side length 2 pi over alpha in x and 2 pi in y, then this number is really the number of square boxes of side length of the short one that you can fit in this rectangle here. So the lower bound, which is, I forgot to say this, but this is the dimension of the unstable manifold of the laminar steady state, the one that Yudovich bifurcated from and Meshalkin-Sinai proved was unstable. This is a computable dimension there, and it's just corresponding to this heuristic that it's growing with the area of this rectangle as you increase the aspect ratio. So as alpha gets really small, this is becoming super stretched, and you can break it up into these motions, which are kind of the smallest motions at the largest scale. So this is the largest, I mean, I don't know how to say it, but this counting argument suggests that this is the right dimension. And I mean, you can prove it. It's just a heuristic thing. Now, the issue with this lower bound is, okay, it can get large as alpha goes to 0. It shows that you become, in some sense, infinite dimensional in the limit as alpha goes to 0. But that actually corresponds to stretching this torus out to infinity. And it's not, somehow that's not really that interesting in terms of what's going on, because it's just that you have a bigger area of the domain, and this area can support many more motions at smaller scales. What would be very interesting, and it's related to Kolmogorov's actual question here, is if you fix the domain and take this Greshov number large, can you get a lower bound that diverges in the limit as mu goes to infinity? And that's a completely open problem. It has been since it was stated. Right. Okay. Are there any questions on this?
Can you restate this open problem, Theo?
Yeah. So the problem is prove that there exists a minimal attractor, or let's just state it for the global attractor. Just prove that there is a lower bound for the global attractor on a fixed domain, a fixed periodic torus, which diverges in the limit as the mu parameter goes to infinity. So it's stated here for nu, but let's just say in general, it's mu going to infinity. Remember, mu is equal to gamma divided by nu square. So if you fix the forcing strength, then if you send nu to 0, that goes to infinity. Okay.
So
okay.
I guess this problem has to do with the number of unstable characteristic exponents for the flow. this dimension of the attractor, and is it known that the number goes to infinity at least? That the unstable manifold
No,
becomes.
It's not known because it's very difficult to actually understand pieces of the attractor. So in this example, one piece of it is well understood. The laminar steady state, which is explicit analytical thing, you can understand perfectly its unstable manifold. And that's in the attractor, so you get this bound. But that's essentially it. There aren't very many other things that we really know about that live in the attractor that you can estimate. But the argument you just made is what's really used to establish the upper bound. So there's some fundamental limitation to that number, which you can prove and give an upper bound, but nothing is understood about how many really there are. Yeah.
Question, is the theorem that you have on the board now, is that for a general 2D flow or for the models we're discussing?
The models we're discussing.
Okay.
Yeah. Okay, so let me conclude with some remarks about this limit and the strong form of the Kolmogorov conjecture. So this is something that I was thinking about just when preparing these lectures, and I was simultaneously doing some numerical simulation, and I saw some interesting phenomena. So let me try to explain. Let's consider a rescaling of the fluid velocity by the ratio viscosity over the forcing strength gamma. Let's call that U tilde. Then if you just plug this into the equation, you see that the way mu, the parameter, comes up is it sits in front of what looks like the Euler equation for U tilde. And then the right-hand side involves the viscosity without any parameter. It's scaled into here, the forcing, and the pressure gradient. So I've just split the pressure. It doesn't matter, but. And now the thing is still incompressible. It still means zero, say. And now I'm just interested in the large mu behavior of stationary states. So let's forget about the time evolving problem for a second. Let's just think about what happened. What's the fate of those branches of stationary states as this mu gets large? So here's a theorem you can prove. I'm sure it's well known to the people who know it well. I mean, it's just that if you have a family parameterized by this mu of stationary states that are H2 of the Navier-Stokes equations, then this rescaling of them converges to a solution of the Euler equation strongly in H1 as mu goes to infinity. And this limit Euler solution, which is H2, solves the Euler equation without a force. Okay, so it's a unforced Euler equation. But the solutions aren't completely general. They have to satisfy an additional constraint. And that constraint is that they live in somehow a band in function space. So in particular, the H2 here is Laplacian U. So this is like the H2 norm square of the solution has to sit between the H1 norm square of the solution and itself with prefactors which correspond to the smallest eigenvalue of Laplacian on the torus and the eigenvalue which you force with. So this is the eigenvalue of this forcing F lambda. So if you force with the gravest mode, which is where you have lambda 1, then this is an equality. So you find that these things, it sits between these two values and there's very little freedom there. And in fact, that's the regime where the laminar solution always stays, and the laminar solution is the example of this theorem. But what the theorem says is that if you force with a higher eigenfunction, then you could have some sort of mixing occurring in the limit, and you can lose mass in this H2 norm. So was there a question?
No, there's a question. I don't understand the notation of the norms. I mean, which is H2 and which is H1? I can't tell from the note.
Yeah. So this is the H2 because this is Laplacian of the velocity in L2 square.
Oh, great. Oh, I see. The triangle's upside down. Okay, good.
Yeah.
All right.
Yeah. So So right. So let me remark that. So on the viscous limit, so along the sequence of viscous things, actually this upper bound holds as an equality. So it turns out that the forcing has the structure that makes this equal when you're on the viscous objects. But then because you only have strong convergence in H1 and only weak convergence in H2, you could have some sort of mixing that causes you to lose H2 norm on the limit. Yeah. And that's why you have this band. And okay, so I'll make some further remarks and show you a picture on the next page.
Well, you have to. Don't you have to do that, no?
You don't have to. There's actually, I mean, there's always, so let me say that there's always one example of this theorem, which corresponds to just the laminar steady state, and that maintains equality for all values. In fact, it's independent of the parameter mu in this setup. So there could be other solutions that you obtain that do have this property, and those are the ones that only converge weakly in H2, but not strongly. Okay. Yeah. So yeah, so this is the laminar one that. Okay, and okay, so now here's a picture that I found from the numerics when I followed this bifurcation curve to very high values of mu. So what I found is that you could trace along a family of steady states that have some basin of attraction. That's actually how I see them numerically. That basin shrinks rapidly as the mu gets large, but you started out as this laminar shear, and then over the course of increasing this thing, you remember you saw it buckle, and it looked like this. There was that buckling, and then it aligns now with these elliptical type vortices that are just sort of anti-aligned with the domain. They have some projection onto the force. They're not orthogonal to it, but they seem to settle onto this profile. And as you increase beyond this point, all that seems to happen is that these things become more localized and more elliptical. And so actually here's an analytical formula that I got by just supposing that the solution in the limit was the sum of two Fourier modes, the one that fits the box in the x direction, the one that fits the box in the y direction. And then you have these elliptical type vortices. Now this picture is not actually an exact solution of the Euler equation. It needs to be modified in some way to make it a solution. It's a solution only if you're on the square box. So it's almost a solution if you're on a box that's nearly square. But in fact, in practice, I checked that this is still almost a solution. The error is quite small. So you could hope that there's actually a nonlinear solution that approximates it. There's some version of this can approximate the nonlinear solution. That's what it looks like. So here's a conjecture based on these numerics. There's a sequence of stationary Navier-Stokes solutions with a non-trivial but shrinking basin of attraction as mu goes to infinity. So if this conjecture is true, then in the particular setting where I did these numerical simulations, which chose a given force and so on, in that setting, the strong Kolmogorov conjecture is false because you always have a fixed point attractor that's a minimal attractor and it's zero dimensional. It's just a point.
So how does this fit with his intuition about why?
Well, actually, let me quote him. So this is the last word of the mini course. Right. So this is from Arnold Kazan book. Kolmogorov always emphasized that the preservation of stability of a steady flow, even for infinitely growing Reynolds numbers, would not contradict hydrodynamical experiments under the assumption that the basin of the corresponding attractor shrinks fast enough. So, and also before I said that he had some doubts about this strong form of the conjecture, this is in line with that. So it's just saying that, yeah, there might be a region of phase space which is particularly simple to understand, corresponding to a branch of steady solutions, but this is a very much shrinking region that you won't see in a typical scenario. And so it doesn't contradict anything about his description of turbulence from that point of view. So, okay, so that's it. And there was more that I would have liked to cover about Euler solutions and stability and instability near them, but I don't have time to do that. I'll just end with this nice picture from well, I know it from Uriel Frisch's book, which shows different approaches to studying this problem of turbulence, approaches of mathematicians sort of stuck at low Reynolds number. There's this renormalization group approach, which I don't know anything about really. And there are all these other things. And I think the moral is just to keep climbing the mountain. So that's it.
Somehow renormalization is somewhere low in this mountain, so it's a low position.
Well, it's much higher than the mathematicians in the, yeah.
Questions, comments?
Well, I forgot them all because you showed the cartoon.
Oh, okay.
But
Oh, I wanted to have a paraphrase of the idea. Either all the minimal attractors go to infinite dimension or something.
Yeah. Or just that they're
at least one goes to infinity, and
yeah,
it has to do with something shrinking fast enough. Can you paraphrase the whole thing? Yeah.
So basically, the conjectures are meant to capture the intuition that turbulence becomes increasingly high dimensional, and so the strong form of the conjecture says all the persistent motions, all the attractors become increasingly high dimensional. The weak form of the conjecture says that some of them do, maybe not all of them do. And what I showed at the end is some evidence for perhaps in some settings an example of an attractor that doesn't. That would contradict the strong form, not the weak form.
So what does that it corresponds to something shrinking? What does that mean?
Yeah. Oh, so the attractor is a fixed point that just moves as you increase the Reynolds number. But as it moves, at each fixed Reynolds number, there is a basin of attraction. It's just that basin of attraction can shrink very rapidly and does with Reynolds number increasing. So for any fixed Reynolds number, it is a minimal attractor and it's zero dimensional. And then as you go to infinity in Reynolds number, it becomes, the basin shrinks to nothing. But nevertheless, along the sequence of Reynolds numbers, it's always a zero dimensional minimal attractor.
Zero dimensional.
And it's just a point.
Yeah. Okay.
Yeah.
Oh, I see. It's an outlier that's not important somehow.
Yeah, it's an outlier that's not important.
And I just want to make a quick comment about this shrinking basin is exactly what we see in pipe flows, which remain linearly stable, but they're still they remain linearly stable for all Reynolds numbers, but you still see the transition.
Yeah, thank you.
I just a stupid question about, can people in experiments make this nu very continuously? So you can really choose the value of nu in experiments?
So the only experiment that I know where you can sort of choose the value of nu is for three-dimensional experiments, and that's in this group at Max Planck in Göttingen. So that's Bodenschatz has a lab. In this lab, he has this like toroidal tube. Inside the tube, he has this sulfur hexafluoride fluid, and he can pressurize this sulfur hexafluoride fluid. So he just applies a pressure in this device. And the point is that as you apply the pressure, the fluid becomes more concentrated, so the density goes up, but the motion is still nearly incompressible. So when the density goes up, the kinematic viscosity of the fluid goes down. So that's the only example that I know of where you can really, aside from just using different fluids in experiments, which is not continuous, like you say, the only example I know of is where you can actually continuously vary that parameter by applying a pressure. Yeah.
So they could also vary nu in time if they wanted.
Yeah.
So, but what is the upshot of this interplay between Euler and Navier-Stokes in dimension 2? So should we think of Euler still as some correct limit in picture for Navier-Stokes, or it completely breaks down? So what is the conclusion of all that analysis?
Yeah. So yeah, that's a good, what?
you repeat the question? I didn't quite understand.
So I'm just wondering, so what is the conclusion whether Euler equation can be still viewed as a limiting picture for the Navier-Stokes as the viscosity goes to zero, as the Reynolds number goes to infinity?
I think there's nothing that we know that contradicts that, but there's also nothing that we know that establishes that. But it's plausible that essentially the behavior, like this attractor, settles down to some infinite dimensional set of solutions of the Euler equation, most of them being far from stationary, and that the behavior of those solutions should mimic the behavior of what we see in two-dimensional turbulence at large Reynolds number. That I think that there's a chance of it happening. I just don't, yeah.
So we can think of Euler as some kind of conservative system, true? So are the ideas of KM applicable to Euler, or is it totally different? So what is, because for KM we kind of anticipate, so this decomposition in the continuous families of ergodic components. And so if it is a limiting picture, then the strong conjecture probably does not have a shot. So is a subject of KM the Euler equation or not?
So I know certain results which use KM to study essentially stability of particular states of Euler, steady states. So you can use KM to construct certain steady states nearby integrable ones, where by integrable I mean the flow lines within the Euler velocity, not as a phase space thing, but really a finite dimensional. So I don't know of an infinite dimensional application of KM to the Euler equations.
There were works by Sergei Kuksin, no, on this?
Yeah, so I mean, there are maybe broad parts of the literature that I don't know.
For Navier-Stokes,
no, for Euler, I guess.
So I mean for Euler. So
yeah.
Because I think that I heard him talking about something like nonlinear Schrödinger or Cartesian de Vries, but not Euler.
If I remember well, but yeah.
So I know that Kuksin has studied a certain invariant measure on Euler solutions, which arises from taking Navier-Stokes, applying a white in time forcing that injects, I mean, this and other methods, but that injects a fixed amount of energy. Then if the forcing is scaled in such a way that there's a balance between the viscous dissipation and the force that's independent of the viscosity, then you have compactness and you can pass from invariant measures of the Navier-Stokes solution to an invariant measure of Euler. And what I know is that not much is understood about that invariant measure for Euler. I know it's known not to be a Dirac, it's not to be like a point masses, but for example, there's no theorem that says it's not supported on like just stationary states, for example, shear flows. There's no such theorem. So I don't know its role in terms of, I don't know enough about it, so.
May I ask about, come back to this question about continuous varying mu. So you said that in the experiments of the Obukhov and others, so mu is also, it's a ratio of the coupling constant for the force over the viscosity and or square viscosity. So you can change the coupling constant of the force if it's electric force, like in experiments of Obukhov and others. That's totally in your control.
That's right. Let me just make this one comment, which is that the laminar solution, if you remember, is like the ratio has a proportionality constant, which is like the ratio of gamma, the coupling constant of the force, divided by viscosity.
Yes.
So in order to obtain solutions that remain bounded, so if you apply a force that's increasing strength, the motion will be increasingly, fast, higher energy. Kolmogorov actually initially suggested that you should couple the two, so that the force amplitude should be taken proportional to viscosity, so that the laminar state in fact has an order 1 prefactor. And then if you do that, then you run into the same problem of having to decrease the viscosity. Otherwise, I think the experiment can be very difficult to run when you have this applied force getting larger and larger.
I see.
Within a, yeah.
So in reality, you have to basically vary both of them, right?
Yeah.
Mm-hmm. I see.
I have a question.
Yeah.
So you've been discussing 2 dimensions because, is it because that's where you can do computations? And can I then, if that were true, can I also then imagine all of these statements and pictures and conjectures can be applied to dimension 3, just as conjectures?
Yes, I think as conjectures, certainly they can be applied to dimension 3. They would be expected in dimension 3. Yeah, as you said, everything I'm doing here is just to make use of some mathematical tools we have in the 2-dimensional setting that we just don't have in the 3-dimensional setting.
Yeah, but you don't know whether a global solution exists in 3D, so how do you discuss attractors?
Yeah, it's just a conjectural thing. Yeah, so Dennis just said in spirit, I think in spirit. So if you were to change the viscosity law in 3D to make it hyperviscosity or something, then you have a well-defined dynamical system globally. And I think the behavior may not be so different. I mean, I don't know. It could be very different, but my personal feeling is that, at least from heuristic point of view, these ideas may not be so closely tied to the issue of global existence of Navier-Stokes solutions.
Which is actually, most people believe it's still true that there is a global solution for Navier-Stokes. Yeah, you may be right.
Well, I mean, I kind of asked this because there was a discussion earlier about deterministic as opposed to statistical, right? And your earlier lectures seem to strongly suggest that we should imagine in dimension 3. To me, they strongly suggested to me, by the way, yes, that we should really imagine the singularities develop quite robustly from the smooth point of view, and that, and even if there is in Navier-Stokes, and even if, I mean, in the Euler, and then in the Navier-Stokes, there, there might be these attractors and all that, but even there, they might not really be deterministic and as nice as you think, but they exist only statistically. And so your orbits are going down into this, it's like a BRS measure. You don't have to imagine that the SRB measure, what Sinai-Ruel-Bowen measure, right? You don't have to imagine that there's really a deterministic system there. I mean, it might not be nice, it might be crazy, but statistically it's there.
Yeah,
it can be statistically and not have a deterministic model. It's statistically it has certain structure. So, because I mean, just saying, singularities seem to be forced on us by your lecture 1 and 2.
Yeah, so as you said, though, those singularities are really emergent in the limit as viscosity goes to 0. So they're singularities of Euler. But as you say, they're even for positive viscosity in 2 dimensions, in fact, where it's known that there are these compact attractors, what's definitely not known, as far as I understand, is the existence of a so-called inertial manifold, which would describe the long time behavior of orbits as shadowing a certain smooth dynamical system on the attractor. So that statement is known for some simpler toy models, but for 2-dimensional Navier-Stokes, that's not known. So in principle, actually, what you said, Dennis, might even be true in 2 dimensions, that the long time behavior doesn't shadow a deterministic smooth system on the attractor, but rather some kind of maybe stochastic system. But it's not clear. I'll be right back. I'm just going to use the bathroom. Just 1 second.
Yeah.
So the question about the existence of an embedding with a global attractor is open into a Euclidean space with the dynamics on it, a smooth one.
Well, so I guess nothing is known about this attractor except that it's finite dimensional. That's my impression from what.
And does it is known that so you said that the existence of an embedding into a Euclidean space, like of any dimension, not necessarily 3, but possibly higher, of the global attractor into a Euclidean space and with smooth dynamics is unknown.
Yeah, I think that the statement about the smooth dynamics is what's not known. It's not known that orbits at long time shadow a smooth dynamics on the attractor.
And in the Banach space of an equation of a solution, is it smooth on it? I mean, sorry, I'm not a specialist of your subject, but
no. So the attractor, you mean is the attractor smooth?
No, I mean, does a dynamic on it? So you got a global attractor in some Banach space, and does a dynamic on it, like in this compact set, is smooth in a Whitney
No, I don't think so. So I think I think that you think of Navier-Stokes as U dot as f of u, so f is the vector field. I think that
of course, yeah.
In 2D, I think that on the attractor, the only estimate known for that f is that it's Halder. So if you take 2 points on the attractor, it's Halder. So it's not known to be smooth.
So like the challenge will be to find a projection into a Euclidean space which make a mapping which is older into a smooth one.
Oh, sorry. Let me walk that back 1 second. The dynamics on the attractor are smooth for finite mu. So if you start on the attractor, the dynamics are well defined and smooth. The issue is just on describing asymptotically orbits that don't start on the attractor, and then the question is, do they shadow some dynamical system on the attractor, not necessarily, the one that comes from restricting to the attractor. Could be
but
some
like
other thing.
what I don't understand is like okay, so you assume you got your global attractor and you look at the flow on it, okay?
Yeah.
And so you unfold it, okay? So you get one more dimension and you just add one to the other dimension of this attractor. So it's still finite dimensional, and then you can project it on an Euclidean space, and so that it is embedded. And
no, but you're describing orbits that start on the attractor, right?
yeah.
But I'm talking about orbits, yeah.
But still, yeah, like it might be a way to see the global attractor as an invariant subset of a deterministic system. Like,
well, it is. The global attractor is an invariant subset of a deterministic system. But
yeah.
But then, yeah, it's a different question than the one of can you describe the long time behavior of any orbit in phase space as some deterministic system on the attractor. Defined on the attractor.
He's using this word shadow. Can you explain what that word means? Because that word was not in Pierre's discussion, and it's in your discussion.
So I just have this picture of, okay, there's this attractor, and then the trajectory approaches the attractor, and I say shadow because the idea would be to find a trajectory living on the attractor that's somehow the shadow of the one that's approaching the attractor and off of it, that will trace the behavior, stay close to the behavior of the trajectory outside for all time asymptotically. So for a long time.
And not in the sense of closeness, but in the sense of statistics. There's a, should be this invariant measure.
Right. So
And
well,
orbits from the outside are behaving statistically according to this measure, the BRS measure, SRB measure, whatever. I mean, when you say shadow, you have to say, I'm wondering what you mean. Closeness?
Oh, no, I actually mean the closeness of the trajectory in this case, but this is not known to be true of Navier-Stokes. So the property that I'm discussing is a property about an individual path.
Yeah.
But perhaps it should be refined to something that's more statistical in nature. Does that answer your question? I'm not sure. Maybe I didn't.
Well, I'm just wondering how reasonable it is, to say it that way, because even if you're in finite dimensions and you have one of these strange attractors and so on, the orbits themselves on the attractor are very unstable.
Yeah, so
it's a chaotic system. So
yeah, I'm saying it that way.
The orbit doesn't behave even on the attractor like two nearby orbits have, after two minutes, they're independent of each other.
Well, but still, if we consider the stable foliation through typical points of SRB measure, well, in the usual situations, and well, in the hyperbolic situations, they can feel, the stable manifolds can feel the whole neighborhood of the attractor.
I see. And then you can find a shadowing orbit then.
Yes.
Okay.
Yes.
Okay. So that's what you mean. Okay. I'm sorry. Okay. You find which stable, your nearby orbit passes through a stable manifold in the normal direction, and then you find
exactly.
Find the orbit. Okay.
Okay, Theo, thanks a lot. So it was very
I have one more comment. I have one more comment about what's known. Suppose you make this assumption that you have plenty of smooth solutions of Navier-Stokes, okay? And then you go pick up this book by Constantine and Foyas, where they're proving under some assumption that's not known like that there's an estimate on, then they can estimate Hausdorff dimensions of attractors. So
yeah.
So there are some conditional results that are known.
Yes.
So
yeah.
Can you, I don't know what's in that book, but can you say something about that?
Yeah, I can. So actually those results are, again, exactly consistent with this Landauâ degree of freedom argument. So the statement is that if you have a well-defined dynamics for the 3D Navier-Stokes, then the Hausdorff,
you have what?
A well-defined global dynamics for 3D Navier-Stokes.
Yeah.
Then the Hausdorff dimension of the global attractor, which exists in that setting, is bounded by essentially the ratio of the size of the period, the box, divided by the Kolmogorov length scale raised to the power 3. Okay, there are some maybe logarithms in the bound, but roughly speaking, that's the estimate. And it's just
here in 2D and in all dimensions, or what?
Well, that 3 is 3 dimensions, so it's raised to the power D, because the idea is, the heuristic idea is that you're filling the torus of side length L, which is LLL in 3D, by little boxes, which corresponds to the smallest scale motion that the flow makes, roughly. That's this Kolmogorov scale.
Okay, so there's a relative theorem known about dimension.
Yeah.
Okay, thank you.
Yeah.
Very nice talk. Thank you.
Thank you. So, well, I hope we will continue some other day, so explore this slope. So now I guess we are on the bunny slope somewhere, way below. So maybe we will reach at some point the green slope.
Okay, that would be nice.
Okay.
Okay.
Take care.
Thanks, everybody.
Bye.